Welcome back to differential geometry. So let's uh, just get started. Okay, so today's topic of interest is differential forms on R3, which corresponds to section 1.6. So in section 1.5, we discussed one forms. So a one form is defined to be it's an expression of the form f dx plus g dy dy plus h dz, where f, g, and h are all they're all differentiable. So we're going to be looking at the more general differential forms on R3. So writing this out, if each summand of a differential form contains p dx sub i's, and since we're working in R3, p ranges from 0 to 3. So the form is called a p form. The form is called a p form. And we say it's of degree p. Okay? So thus, we're going to write our forms like this. A zero form, it's just a differentiable function. Okay, function f. A one form, that is an expression. Well, we already defined it, of course, but it's of the form f dx plus g dy plus h dz. Okay, a two form, that is an expression of the form f dx dy y plus g dx dz plus h dy dz. And we're also saying that f, g, and h are still differentiable functions. And finally, a three form we're going to define. And that would just be an expression of the form f dx dy dz. And we'll go into a little bit more about how we deal with dx, dy, dz's. That is the product of the differentials and differential forms. So what we're going to do now is talk about how we can multiply. Well, we'll talk about how we can multiply and add differential forms. So first of all, we can do so. We can add and multiply by differential forms. Okay, so and these operations obey associativity and distribution laws, or distributive laws. Okay, these. But they're not commutative. Okay, but are not commutative. So they're actually anti-commutative. Just like the cross product, for example. So writing this out more explicitly, by anti-commutative, I mean dxi dxj is equal to negative dxj dxi. Okay. And so this leads to the following result. So of course dx of I is equal to 0. And this is because we know that dx sub I is equal to negative dx sub I. And 0 is the only number that fits that criteria, right? So in other words, if we have any repeats of differentials, they're just going to be 0. So, quick example. So simplify the differential form. Simplify 3 dx dy dx. Okay, so to do this, first we know that dy dx is equal to negative dx dy. So this is equal to 3 dx negative dx dy. Okay. So by associativity, we can write that this is equal to negative 3 dx dy. And again, by associativity, we can just write negative 3 dx is 0. So 3 times 0 dy. So this is just equal to 0. Okay, so in other words, we can easily show that if p is greater than 3, all p forms in R3 are just going to be 0. Okay, so multiplication of forms is generally denoted by the wedge, okay? And that wedge is drawn like this, so multiplication of forms denoted by a wedge like that. Okay? And the product of two forms is said to be a wedge product. So if we go back to like the past example, we can tell we're being a little bit lazy with notation, because we could write the 3 dx dy dz, it would just be the product of the forms 3 dx with dy wedged with dz, for example. But I'm just going to show you a quick example of the algebra behind involved when we multiply out forms. So let phi equal x squared dx plus y dy, and psi, let that be equal to dx minus x dz. Then phi wedge psi is equal to, well, just plugging the psi and phi in, x squared dx plus y dy wedged with dx minus x dz. Okay, and then now I'm going to use distributivity. So that's x squared dx dx minus x cubed dx dz plus y dy dz minus xy dy dz minus xy dy dz. Okay, and just cleaning this up a little bit, the dx is 0, so we're going to lose this one, of course. And oh, sorry, I made a mistake here. It should be dy dx here. Okay. Anyways, this is equal to negative x to the third dx dz minus, because we're flipping these two, minus y dx dy minus xy dy dz. Okay. So we could also calculate uh, psi cap phi. And if we did that, we would find that it's equal to negative phi cap psi. Okay. But this is actually true in general for one forms, which we can just show right now. So, lemma 6.2. So if phi and psi are one forms, then phi cap psi is equal to negative psi cap phi. Proof. Okay, so we write that phi is equal to negative f sub I dx sub I, and psi is equal to some g sub I dx sub I. So phi cap psi, that's equal to some f sub I g sub j dx sub I dx sub j. dxj. Okay, and we can just flip them. That is flip the dx sub I and the dx sub j. That's so we get negative sum fi gj dxj dxi, which is so we get negative sum g sub I f sub I dxj dxi. I probably could have done that in one step, but it's fine, which is equal to negative psi cap phi. Okay, so that concludes the proof. So now I have a question. So does this relation hold for two forms? So, but if we do this for two forms, we wouldn't be able to work in R3 because that would form a 4 form, which is going to be 0. So we're just going to assume that n is greater than 3 in this case. So, okay. So say we are working in Rn temporarily, and say where n is greater than 3. So we're going to write that phi is equal to sum f sub ij dxi dxj, and psi is equal to sum g sub ij dxi dxj dxi dxj. Okay, I dxj. So we can write that, and this is pretty much very similar proof to the last one. Phi cap psi, that is equal to the sum f sub ij g sub j, kl dxi dxj xi dxj dxk dxl dxk dxl. Okay, so we're going to perform 4 transpositions. So 4 negatives make a positive. So this doesn't change the sign. And we're just going to flip the g sub kl and the g sub I. Well, we're just going to flip the order of these two terms. So we get the g sub kl f sub ij, that this is equal to this, times dxk k dxl dxi dxj. Okay, and what is that? Well, that's psi cap phi. Okay. So in other words, two forms commute under the wedge product. So that's interesting. But what about in general? Well, I haven't figured that out yet, but, well, that's left to you. So, see you next time. Thanks for listening and watching.